To determine the appropriate protection and wire size for a parallel bank of 6-phase converters feeding a 250 amps alternating current chiller unit, several factors need to be considered. We'll start by calculating the total load current, followed by the branch circuit current, and then select the appropriate circuit protection and wire size, while also keeping in mind some additional factors. Firstly, determine the total load current, which is the sum of the phase converter currents. Given that each of the 6-phase converters has a full load current of 360 amps, the total load current is calculated as 6 times 360 amps, which equals 2160 amps. Secondly, calculate the branch circuit current. According to the National Electrical Code, motor circuits must be rated at 125% of the full load current. Therefore, the branch circuit current is calculated by multiplying the total load current by 1.25. So 2160 amps times 1.25 equals 2700 amps. Now we move on to selecting the appropriate circuit protection. For overcurrent protection, use a circuit breaker or fuse switch with a rating equal to or greater than the calculated branch circuit current. In this case, you should use a circuit breaker or fuse switch rated for 2700 amps or higher. Next is selecting the appropriate wire size. Consult the National Electrical Code Table 310.16 for wire sizes based on the circuit current and conductor type. For a current of 2700 amps, 500 kcmil copper conductors would be appropriate. It is imperative to consult the latest version of the National Electrical Code for the most up-to-date requirements and conductor ampacities. Now, let's consider some additional factors. Ambient temperature is a critical consideration. The ampacity of conductors decreases as the ambient temperature increases. You might need to adjust the wire size if the installation location has a higher ambient temperature than what is listed in the National Electrical Code tables. Consult the correction factors in the National Electrical Code to determine the appropriate adjustment. Conduit fill is another important consideration. Ensure that the chosen wires fit within the conduit without exceeding the allowable fill percentage as specified in the National Electrical Code. Overfilling a conduit can lead to overheating and potentially dangerous situations. Voltage drop is another thing to consider. Calculate the voltage drop in the circuit to ensure that the chiller unit receives adequate voltage. Excessive voltage drop can cause the chiller to malfunction or operate inefficiently. The National Electrical Code provides guidelines for voltage drop in branch circuits and feeders. Now let's look at some specific considerations. Each motor starter for the phase converter should be rated for the full load current of the corresponding phase converter, which is 360 amps in this case. The chiller starter should be rated for the chiller unit's current rating, which is 250 amps. Parallel operation is also important. Ensure that the phase converters are properly parallel to share the load evenly. Improper paralleling can lead to unequal load sharing and potential equipment damage. Finally, load balancing. Use a load balancing relay or other device to ensure that the converters share the load equally. This will help to prevent any one converter from being overloaded. To summarize, firstly, determine the total load current by summing the currents of all phase converters. Secondly, calculate the branch circuit current by multiplying the total load current by 1.25 to account for the 125% rule for motor circuits. Thirdly, select a circuit breaker or fuse switch with a rating equal to or greater than the branch circuit current to provide adequate overcurrent protection. Fourthly, consult the National Electrical Code Table 310.16 to determine the appropriate wire size based on the calculated current and conductor type. Fifthly, adjust the wire size as necessary based on the ambient temperature, using the correction factors provided in the National Electrical Code. Sixthly, ensure that the chosen wires fit within the conduit without exceeding the allowable fill percentage as specified in the National Electrical Code. Seventhly, calculate the voltage drop in the circuit to ensure that the chiller unit receives adequate voltage. Eighthly, ensure that each motor starter is rated for the full load current of the corresponding phase converter. Ninthly, verify that the chiller starter is rated for the chiller unit's current rating. Intently ensure that the phase converters are properly paralleled and use a load balancing relay to ensure equal load sharing. By following these steps, you can ensure that the protection and wire size for the parallel bank of phase converters are appropriately sized, providing safe and reliable operation for the chiller unit. Always refer to the latest edition of the National Electrical Code and consult with a qualified electrical engineer or electrician for specific installation requirements and to ensure compliance with all applicable codes and regulations. The National Electrical Code provides specific tables and guidelines for determining the ampacity of conductors based on their size, insulation type, and installation method. Table 310.16 is a commonly used table for determining the allowable ampacity of insulated conductors rated up to 600 volts, installed in raceways, cable trays, or directly buried in earth. The table provides ampacity values for various conductor sizes and insulation types at specific operating temperatures, typically 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius. When selecting a conductor size, it is essential to consider the ambient temperature and apply any necessary correction factors. If the ambient temperature exceeds the temperature rating of the conductor, the ampacity must be derated to prevent overheating and potential damage to the insulation. The National Electrical Code provides correction factors for various ambient temperatures, which must be applied to the ampacity values listed in Table 310.16. In addition to ambient temperature, the number of conductors in a raceway or cable also affects the ampacity of each conductor. When multiple conductors are installed in close proximity, the heat generated by each conductor can raise the overall temperature within the raceway or cable, reducing the ampacity of each conductor. The National Electrical Code provides adjustment factors for the number of conductors in a raceway or cable, which must be applied to the ampacity values listed in Table 310.16. When determining the appropriate wire size for a motor circuit, it is also essential to consider the motor's full load current, starting current, and duty cycle. Motors typically draw a much higher current during startup than during normal operation, which can cause a significant voltage drop in the circuit. To prevent excessive voltage drop, the wire size must be large enough to handle the motor's starting current without exceeding the allowable voltage drop limit specified in the National Electrical Code. The National Electrical Code provides guidelines for calculating the voltage drop in motor circuits, which take into account the motor's full load current, starting current, conductor length, and conductor impedance. The National Electrical Code also specifies the minimum size of conductors for motor circuits based on the motor's full load current. Table 430.22 provides the minimum conductor size for single motor circuits, while Table 430.24 provides the minimum conductor size for multiple motor circuits. When selecting a circuit breaker or fuse switch for motor protection, it is essential to consider the motor's full load current, starting current, and overload protection requirements. Circuit breakers and fuse switches are designed to protect motors from overloads, short circuits, and ground faults. The National Electrical Code provides guidelines for selecting the appropriate circuit breaker or fuse switch size for motor circuits, which take into account the motor's full load current, starting current, and overload protection characteristics. The National Electrical Code also specifies the maximum size of circuit breakers and fuse switches for motor circuits based on the motor's full load current. Table 430.52 provides the maximum size of circuit breakers and fuse switches for single motor circuits, while Table 430.53 provides the maximum size of circuit breakers and fuse switches for multiple motor circuits. In addition to overcurrent protection, motors also require overload protection to prevent damage from sustained overloads. Overload protection devices, such as thermal overload relays, are designed to trip the circuit if the motor draws excessive current for an extended period. The National Electrical Code provides guidelines for selecting the appropriate overload protection device for motor circuits, which take into account the motor's full load current and service factor. The National Electrical Code also specifies the maximum setting of overload protection devices for motor circuits based on the motor's full load current. When installing electrical equipment, it is essential to follow all applicable codes and regulations, including the National Electrical Code. The National Electrical Code is a comprehensive set of standards and guidelines for the safe installation of electrical wiring and equipment. Compliance with the National Electrical Code is essential to protect people and property from electrical hazards. In addition to the National Electrical Code, local codes and regulations may also apply to electrical installations. It is essential to consult with local authorities to determine the specific requirements for your area. When working with electricity, it is essential to take appropriate safety precautions. Always disconnect power before working on electrical equipment and use appropriate personal protective equipment, such as gloves and safety glasses. If you are not qualified to work with electricity, it is essential to hire a licensed electrician to perform the work. Working with electricity can be dangerous, and it is essential to take the necessary precautions to protect yourself and others from harm. Always double-check every wire, connection and setting of overcurrent protection to ensure that the full installation is per the manufacturer's specifications as well as the local and national electrical codes. This should be a standard operating procedure prior to commissioning any new or altered electrical equipment. It is also worthwhile to keep a log of all electrical equipment, including equipment settings, wire sizes, and any other pertinent information for future reference. This can be very helpful if troubleshooting is needed in the future, or if equipment needs to be replaced. Proper documentation is key to a well-maintained and safe electrical system. Remember, safety is paramount when working with electrical systems. Incorrectly sized wires or overcurrent protection can lead to overheating, fire, and equipment failure. Always consult the latest edition of the National Electrical Code and work with qualified professionals to ensure safe and reliable electrical installation. Moreover, consider the future expansion of the electrical system. It is wise to install slightly larger conduits and wire sizes than currently required to accommodate future load increases. This foresight can save significant time and money in the long run, avoiding costly upgrades when additional capacity is needed. Regularly inspect and maintain the electrical system. Check for loose connections, damaged insulation, and signs of overheating. Use thermal imaging to identify hot spots and address them before they become major problems. A well-maintained electrical system not only operates safely but also performs more efficiently, reducing energy consumption and extending the lifespan of the equipment. Consider implementing energy-efficient technologies. Replace old motors with high-efficiency models, install variable frequency drives to control motor speed and reduce energy waste, and use LED lighting to lower electricity consumption. These upgrades can significantly reduce energy costs and contribute to a more sustainable operation. Train personnel on proper electrical safety procedures. Ensure that all employees who work with or around electrical equipment are properly trained on how to identify hazards, use personal protective equipment, and respond to electrical emergencies. Regular training sessions reinforce safety practices and promote a culture of safety within the organization. Keep accurate records of all electrical work performed. Document all installations, repairs, and modifications to the electrical system. This information is invaluable for troubleshooting, maintenance planning, and future upgrades. Accurate records also demonstrate compliance with safety regulations and provide a basis for continuous improvement. Establish a preventative maintenance program for the electrical system. Schedule regular inspections, testing, and cleaning of electrical equipment. This proactive approach helps to identify potential problems before they lead to failures, minimizing downtime and ensuring reliable operation. In summary, correctly sizing the protection and wiring for parallel phase converters feeding a chiller unit requires a comprehensive understanding of electrical codes, motor characteristics, and safety practices. By following the steps outlined in this discussion, you can ensure a safe, reliable, and efficient electrical installation that meets the demands of the application. And remember, always consult with qualified professionals to verify your calculations and ensure compliance with all applicable regulations. Also consider the impact of harmonic currents generated by the phase converters. Harmonic currents can cause overheating of conductors and transformers, as well as malfunction of sensitive electronic equipment. Install harmonic filters to mitigate these effects and ensure a clean and stable power supply. Regularly test the grounding system to verify its effectiveness. A properly grounded system is essential for protecting against electrical shock and preventing equipment damage. Use a ground resistance meter to measure the resistance of the grounding system and ensure that it meets the requirements of the National Electrical Code.